Kia ora koutou katoa. My name is Richard Patterson and I'm a network architect for Sky over in the UK. About 5 years ago, I spoke at UK NOF about how we had just recently finished building and had launched a brand new Greenfield fixed line broadband network over in Italy for Sky Italia. I covered how we're using unbundled GPON in the access network through to EVPN to carry the Ethernet frames across our metro networks, segment routing in the core, and finally the BNG or subscriber termination layer, where I touched on the use of MAP-T for IPv4 address sharing. That network in Italy has been growing quite rapidly over the last few years. We have almost, not quite 100% of all customers over there using MAP-T now. So MAP-T has been working well. We've decided to bring that over to the existing UK network. So there are things that are different in a Brownfield deployment and that's compared to a Greenfield deployment, which we'll get to in a moment, but a quick recap on what MAP-T is. So mapping of address and port using translation. It's one of the few IPv4 as a service technologies, which is basically a colloquialism for delivering IPv4 connectivity over IPv6 or using IPv6. They all generally also have the ability to do IPv4 address sharing as well. So you can group these IPv4 as a service technologies into the ones that are using translation versus encapsulation. Those that are using translation can be further distinguished by ones that are doing stateful versus stateless NAT64. And then are they using traditional stateful carrier grade NAT for IPv4 address sharing or the newer algorithmically done address plus port technology? That's stateless. They all have their pros and cons. So to help you evaluate which is best for your use case, you can check out RFC 9313. So MAP itself comes in two flavors. There's the encapsulation version, which has more per packet overhead because you're whacking an entire V6 40-byte header on top of the V4 payload. But the IPv4 header remains intact when it pops out the other side. The translation version, there's fewer bytes of overhead, not zero. It's because you're swapping the 20-byte V4 header for the 40-byte IPv6 header, or 48 if you include the V6 fragmentation header. And that translation isn't lossless. So there are attributes and options within a V4 header that just don't exist in a V6 header. It does, however, leave the layer 4 header exposed if for any hashing or inspection you may need to do. And one of the features I think is quite cool is that the translation to the V6 destination is predictable. So you can address your CDNs and other servers and stuff out of that predictable range, and you can get this thing I call border relay bypass, where you can serve IPv4 only eyeballs from IPv6 only content servers. As mentioned, the UK deployment is a slightly different topology to our Italian deployment. In Italy, we went to RFP for everything. So when we did the BNG selection, we chose a BNG that could do MAP-T border relay function natively on it. In the UK, we already have our BNGs. They don't support this function. So we went for an off-box border relay solution elsewhere in the network. Again, it's more of a traditional network compared to Italy. In Italy, we got to use EVPNs and segment routing. In the UK, it's more of a traditional network with targeted LDP pseudowires to the BNG and then 6PE across from the BNG to the border relays. The border relays themselves, they're actually a two-box solution that we've gone for. The absolute majority of traffic is translated by a Lightspeed Plus based Cisco ASR 9903. But there's still a small percentage of traffic that needs to be punted off box to an exception handler for special treatment. And this is the Catalyst 8500 that we're using for that function. Now, there's quite a few packet types which could be considered exception traffic, depending on your vendor selection. With the Lightspeed Plus, we're quite lucky in the sense that it can handle most things in hardware natively on the Lightspeed Plus. The only things that really get punted off to the Catalyst 8500 are packets that are too big and need fragmentation, or packets that are already fragmented and need reassembly for translation. In UK, our whole network is built around 4 supercore sites where we have a BGP-free pure P layer. All of our border relays are hanging off, our PEs hanging off those P nodes in those 4 centralized supercore POPs. We haven't, depending on the traffic, how the traffic behaves going forward, we haven't decided whether we're going to scale that solution horizontally at those 4 sites, or whether we distribute and we put more border relays closer down to the subscriber to 31 satellite POPs where we also have BNGs. It doesn't really make any sense to go beyond that, beyond the BNG, because packets need to be routed via the BNG anyway. So because MAP-T is stateless, we can do things like anycast for resiliency. So we anycast all of the IPv6 prefixes from all of the border relays southbound to the BNG, and we anycast all of the v4 prefixes northbound to the pairing transit and CDN and what have you. So flows, ingress and egress flows can be asymmetric and go by any of these border relays. Likewise, because it's stateless, and now that we're using anycast, we can actually use ECMP for load balancing across devices as well. So because there's no need for expensive state signaling, multiple flows to one user, end user can go via multiple BRs at different locations. This did, however, raise an issue that we had in our network, which was our pairing transit vendor hashes fragments differently. So the initial fragment with a layer 4 header can get hashed one way, in this example, up via Telehouse London, and then all the subsequent fragments that don't have a layer 4 header will get hashed differently and could end up on completely different border relays. This is actually probably the main reason why we haven't quite got to 100% of MAP-T footprint in Italy. Not because we don't anycast in Italy, but the same hashing algorithm is generally used across a chassis for all types of hashing, including across lag bundle members. So yeah, even though we're not using anycast from different border relays in Italy, the fragments may land on different line cards or indeed different ASICs on the same line card. We've mitigated this problem by going around our UK network and enabling layer 3 only hashing. Hopefully at some point we'll go back to Italy and retrofit that and finally be able to turn off dual stack and DHCP4. Now, the anycast doesn't just follow the IGP shortest path. We use BGP policies to steer traffic to the closest or the most optimal border relay. Subscribers that terminate in the supercore BNGs right next to a border relay, they'll use those border relays, local ones, as primary. If that fails, then flows will fail back across to the remaining 3 sites evenly. And for subscribers that terminate in those satellite POPs further down the network, they tend to use prefer the 2 border relays at the parent supercore sites that satellite POP parents to. If we do decide to go distributed, then that one will pick up as primary, and only if that one fails will the 2 parent supercore POPs pick that up. Just to help visualize that, a subscriber terminated in Telehouse London would prefer Telehouse London under BAU. Unless it were to fail, flows go to the other 3 sites. Subscriber terminating a satellite POP would prefer both Telehouse London and Brick Lane if they were both active. One's failed, so the other one picks up the slack. And if we go to distributed, the distributed one is primary unless it were to fail. So the statelessness, or MAP-T being stateless, is great because it allows us to use cheaper, more scalable hardware. Allows us to use anycast for resiliency and ECMP for load balancing. But to get that statelessness, the complexity has been removed from the forwarding plane, and it's had to go not into the control plane, but into what I call the administrative plane. So unlike traditional carrier-grade NAT methods, which will dynamically and efficiently allocate ports as required, in map gets its statelessness by using a predetermined algorithm plus a configurable map rules to bind the user's v6 prefix to a v4 address and a port set ID. Now that binding is fixed, so it's a fixed sharing ratio. In Italy, we use a 16:1 sharing ratio. In the UK, we've gone for an 8:1 sharing ratio. Not for any technical reasons. You could absolutely push this much higher than even 16:1 if your local regulations allow it. So the 8:1 sharing ratio profile is our default, which we expect the absolute majority, 90-something% of customers to be in. But we also have a 1:1 profile, which we're still using MapT to deliver IPv4 as a service instead of falling back to dual stack, but that customer still gets the entire v4 address to use for themselves. We've built 2 processes so that customer can opt out of address sharing to the 1:1 profile. We put a lot of effort into developing a automated or proactive opt-out approach. This is where we listen to notifications that are being sent by the CPE, the Sky Hub, or the My Sky app, whenever a user toggles UPnP or DMZ or does port forwarding. We will apply the 1:1 profile. We'll have to disconnect the customer because they need to reconnect to obtain a new DHIPv6 lease with a different set of MapT rules. And there's also a reactive journey as well for humans to manually be able to do it. We use port-based authentication for all of our subscribers. This means we don't pay attention to any usernames or passwords or anything. We look for information that is inserted by the access node into the DHCP messaging, specifically the remote ID, which is DHIPv6 option 37, and in v4 it's option 82.2. In dual stack land, either v4 or v6 could trigger authentication, but in MapT we rely on DHIPv6, so we should really only be seeing DHIPv6 for this. In Italy, Greenfield network deployment, we had no legacy technical debt. We knew that all CPEs we were sending to customers supported MapT, so we could forcibly use MapT, force MapT on them. In the UK, we've already got an existing over 6 million customers. We have to be a bit more graceful and or opportunistic with our enablement process. So we rely on a CPE that supports MapT, asking for MapT, and then we'll give it a DHIPv6 lease with MapT options. It asks for MapT by including the standard MapT option, option 95, in the DHIPv6 option request option in the DHIPv6 solicit. However, only about 70% of our wholesalers' access network actually supports lightweight DHIPv6 relay agent, or LDRA, which is required to insert that information into the DHCP messaging. So we have, for about 30% of these customers, we have to rely on DHIPv4 to bootstrap authentication, and then we can go through v6 and give them MapT. We obviously don't want to burn any more public IPv4 addresses than we have to. So for these bootstrapped v4 sessions, we give them a private RFC 6598 address, which is not usable. So we were relying on DHIPv6 option 95 before to tell us that that CPE supports MapT. Option 95 doesn't exist in DHIPv4, so we had to get creative. We already use option 60, or vendor class ID, for a bunch of other things. So we appended a MapT string on the end of that so that we could signal inside DHIPv4 that, hey, this CPE itself supports MapT. We also saw during our trials that there are CPEs out there that don't support MapT, but still ask for MapT by including option 95. OpenWRT's DHIPv6 client is the main culprit for this. So whilst it's greedy by default, it includes a whole bunch of options. So they will get a v4 lease that's broken, and they'll also get v6 lease, and they'll have working v6, but we'll expect them to use MapT, which they won't. The good thing about OpenWRT is it does actually support MapT, but it's not installed by default. So you have to install the map package to get MapT working. So that's an easy fix. The long-term fix would be for us to change the default behavior of OpenWRT's DHIPv6 client. Now, Ubiquiti's Unify routers also use OpenWRT's or the same DHIPv6 client, but they don't have a map package. They don't support MapT. So the only real user fix that they can do, or users can do there, is to disable IPv6 to force DHIPv4 authentication. The alternative is they can escalate sufficiently through our call center and then hopefully be able to disable MapT on the network side. So again, to help visualize this logic, this authentication logic, either DHIPv6 or v4 can trigger an authentication request. The first thing that Radius does is check to see whether we've actually finished enabling and configuring the BNGs to know about MapT, which we have done now. Our entire BNG estate does support MapT. So the next thing it does is check for the presence of that option 95. If that DHIPv6 option 95 doesn't exist, it then looks and does a regex match for that string in DHIPv4 option 60. If either of those exist, then it checks for the disable profile, followed finally by should they be opted out to 1-to-1 or use the default 8-to-1. CDN steering is another thing, well, it's a thing that sort of becomes a bit more challenging in this IPv4 as a service world, or indeed even a traditional carrier-grade NAT world where your IPv4 topology is different from your IPv6 topology. So we've got CDN caches quite deep into our network at those satellite pops I mentioned earlier. So the happy path for IPv6 eyeballs is that we'd steer them directly to their closest CDN cache. The unhappy path then for IPv4 eyeballs is that we'd still use that same CDN cache, but that gets tromboned back up to our centralized sites where the border relays are for translation before coming back down again to the subscriber. Some CDN providers use the source address of a DNS query for these steering decisions. eDNS, and it's usually the recursive name servers, which isn't very helpful. eDNS client subnet, ECS, has come along, and that embeds the original source IP of the query into the payload so they can make more informed decisions. However, this doesn't really help us in this situation. So what the authoritative name servers need to do these days now is to actually make decisions not just on the ECS value, but also the query type. Is the query type for an A record for v4, or is it query type a quad A query for v6, as well as the ECS value? So until such time as the CDN and authoritative name servers just do that and catch up, it's going to take a while. We're having to do the logic for them. So we have 6 Anycast sites for our recursive DNS platform. We're only giving these MapT customers the v6 VIPs for recursive DNS. So the DNS queries are always going to come over IPv6 to our recursive name platform. It does that logic I just mentioned. So it checks to see whether the query type, if it's for a quad A, it'll just insert the v6 ECS value as normal. But if it's an A record query, then it will do a lookup internally. It'll try and find out the MapT IPv4 address that that customer is using, and it'll synthesize that IPv4 ECS value before forwarding it up. So again, happy path now for both. IPv6 eyeballs can go direct to the local CDN cache, but IPv4 eyeballs can be steered towards the centralized CDN cache. We now have a vested interest in making as much of our content as possible IPv6. So both of our flagship video products, Sky Glass and Sky Stream, are now supporting IPv6 since QS031, which is already live. I mentioned that the complexity has been moved from the forwarding plane before to the administrative plane and the complications of that. Now your IPv4 consumption is directly tied to the IPv6 consumption, your DHIPv6 pools. So previously, we had automation for our DHIPv4 pool management. So we had really granular DHIPv4 pools to get the most efficiency out of them, and that required a lot of automation to shuffle things around all the time. But then in v6, we just threw a massive, big, large IPv6 prefix into the DHIPv6 pool, enough to satisfy the whole scale of the BNG, and then we didn't have to worry about automation. If we were to do that with MAPT, or with this, then that large IPv6 prefix would consume a whole bunch of IPv4 that we don't necessarily want to waste. So automation is important for MAPT these days. One of the complaints I hear from other CPEs who are interested in MAPT is there's a lack of MAPT support on CPEs. So we were lucky enough to build an in-house device using the open source RDKB, but OpenWRT, despite the issue I mentioned before, is also a very great solution. As I mentioned, the map package isn't installed by default, and there's also a recent bug that's been introduced by the migration from IP tables to NetFilter, which I'm sure they'll fix at some point. Kinetic, these guys were really proactive. They reached out following our launch in Italy, and they now have their own support in their devices. And the Fritzbox. These guys have been hard at work to build their own support in Fritz, which is awesome. It's in the lab version now. If you go into the WAN IPv6 settings and tick that box, it will work for you. And apparently, TP-Link and Zixel also have support, which I have not been able to validate or test myself. That's all the main content. I wanted to end on this last little bonus slide, which is unexpected DDoS protection. So packets that come in that are malformed will just hit our border relays, not be translated, and just drop on the floor. So yeah, bonus DDoS protection.